Okay.
We also assume it's your.
All right, let's get started. Okay. How did everything go? Oh, hold on. That's the one we're supposed to be on. So I just had my template there. Okay. How did everything go with homework 3.2? That was the second Truss homework, and that was the one on the pre-recorded lecture. I don't really think there was anything majorly conceptually different from the 3.2 to 3.1, other than this homework assignment had members that were all of the same slope ratio, and this one had members of different slope ratios. So it just added on the bookkeeping requirements a bit. But I think my overall point should be, it shouldn't have been any more difficult, right? Anybody have any issues with that? Okay, good deal. Couple things, attendance grades, they're up to date. I've been doing, I think I said at the start of the semester I'd try and update attendance grades probably once a week, but here recently I've been finding time to just be able to do it right before class. So your attendance grades should be up to date as of today. A couple announcements on scheduling. We have a celebration of learning on September 25th. Okay, that's 2 weeks from today, so it's on Monday. So we're going to have an exam review on the 22nd. I'll talk to you more about how I do my exam reviews as we get closer, but the long story short of it is I spent a few minutes finished chatting about the exam, and then I want you to come prepared to ask your questions. So we can talk about homeworks, concepts, whatever you want, but just on exam review day, come prepared to ask questions, okay? And that first exam will cover everything up through truss deflections. So we're on plane truss analysis 3, we'll have plane truss analysis 4, then we'll have 2 deflection lectures, and then that'll be the content for exam 1. Okay. Any questions? Okay. All right. So today we're going to continue our discussion on trusses, and I would say for the most part we've sort of addressed everything associated with the method of joints, other than sort of the 2 things. One of them is I mentioned something during one of our examples. I said, whenever you're applying the method of joints, you can solve for at most a joint that contains at most 2 unknowns. And I said that because we are limited to 2 equations of equilibrium per joint. Okay, so two equations, 2 unknowns. That's why we dealt with. That was our limit for the method of joints. But I said something in one of our examples. I said, for now, I kind of want you to only pick joints that have 2 unknowns, but not 2 diagonal unknowns. I said, try and avoid that. And there was a reason for that. It makes the math a little bit more involved and a little bit more difficult. But on some trusses, it's unavoidable. And so I want to make sure that we're comfortable analyzing a joint with 2 unknowns, and those 2 unknowns both happen to be diagonals. I'm also going to show you today a little trick for making truss analysis a little easier. If you recall in my pre-recorded lecture, we had a truss that was a little bit more involved, but something happened that was kind of interesting for our very last member in that truss analysis. Remember what the force was in that very last member? 0. There was 0 force inside that member. And so one thing that you can do to speed up a truss analysis is to quickly identify members that contain 0 force. And there are ways to do that, and I want to show you that today. Now, in order to solve a joint that has 2 diagonal unknowns, what we have to do is we have to utilize some simultaneous equation math from algebra in order to solve that joint. So I want to go back to that from algebra. Okay, so let's go back to Math 127 or Math 130, or if you had it in high school. I want to go to this problem here. So let's say I give you 2 equations with 2 unknowns. Okay, so let's keep it simple. Let's say we have x plus 2y equals 3, and I have 2x plus 3y equals 4. Okay. The goal is to try and find these 2 magical values, this one magical value of x and this magical value of y, that satisfies both equations, okay? And I'm going to tell you that this is the answer. X is -1 and Y is 2. And if you don't believe me, you can just plug and chug. So on the first equation, I have -1 plus 4 is 3. That's true. And I have -2 plus 6 is 4. That's true on the second one. And I propose that that is the only pair of numbers that will satisfy both equations. Okay? Now there are a number of ways that you can solve this. I would propose that there are 3 practical ways that you can do it. The first 2 are sort of a review. They're probably what you're familiar with, either from high school or college algebra or pre-calculus here at Marshall. But I kind of want to show you the third one just to kind of make sure that we're all familiar with this. So let's start off with our first method that I'm going to review, which is substitution. Okay, so substitution, what that means is this. So what I'm going to do is I'm going to take one of these equations and I'm going to isolate one of the variables. Okay, so let's just take the first equation. So the first equation says that x plus 2y equals 3. So I'm looking at the coefficients. I'm thinking it's probably going to be a little easier to isolate x. So I'll subtract 2y on both sides, and I get x equals 3 minus 2y. So that's a fact. I know that whatever x is, it equals 3 minus 2y. And what I'll do is I'll take that expression and substitute it into the second equation. So the first equation, I isolate the variable. The second equation, I take that isolation and I substitute it in. So that second equation is 2x plus 3y equals 4. Well, instead of x, I'm going to put 3 minus 2y. Okay? Distribute that out. So 2 times 3 is 6. 2 times 2 is 4. So I have 6 minus 4y plus 3y equals 4. 6 minus y equals 4. I get y equals 2. And then I can take that 2 and I can plug it into either equation. It doesn't really matter. I'll plug it into the first one. So we'll say x plus 2y equals 3. So instead of y, I put in the 2. I get this, x is minus 1. And that's the answer. Okay? And I have a feeling that you all have has everybody done a problem like that before? It's probably been a while, but everybody's done a problem like that at some point or another. Am I correct? Okay. So that's our first method of solving a simultaneous equation, is substitution. Okay? The next method is elimination. Okay? Now the way elimination works is what I do is I take one of the equations and I try and identify a magic number to multiply the entire equation by. So what I'm going to do is I'm going to take this first equation and I'm going to multiply the whole thing by -2. So multiply the left side of the equation by -2 and the right side of the equation by -2. So instead of x plus 2y equals 3, I'm going to get -2x minus 4y equals -6. And the reason that I did that is because what I'm trying to do is I'm trying to match one of the coefficients in the other equation. So I picked -2 because if you look at the other equation, so the first one yielded a -2 in front of x. This equation already had a +2 in front of x. So what I can then do is take the entire set of equations and add them together. And what we'll see is that the x's cancel. So I have -2x plus 2x is 0. Over here I have -4y plus 3y is -y. -6 plus 4 is -2. So I get y equals 2. Then I can take that and substitute it in. Same way I did before, get the same solution. Okay? Everybody with me on that? Now those are probably the 2 methods that you are familiar with from either high school algebra or college algebra. Everybody has seen that at some point or another, am I right? Now, that'll work, and I'm not saying that you can't apply those methods in here. They'll work just fine. The only thing that's worth mentioning is that for the joints and whatnot that we're going to be analyzing, these coefficients end up not being like 2s or 3s. They end up being the sine of 36 degrees or, you know, the square root of 3 over 2. So the actual numerical coefficients end up being a little messier, and sometimes it's a little easier to just surrender to the process and maybe let a little bit of technology take over. So the third method is to use matrix algebra. Okay. Okay. And the way that works is we take our equations and we rewrite them in matrix form. Okay. And so the way that works is, I'll sort of do this down here just to make sure everybody's on the same page. I have a square matrix of coefficients I have my unknowns, and then that equals my coefficients on the left side or on the right side of the equation. Now over here it's pretty easy. It's just 3 and 4, okay? And what I do over here is I say I'm going to write this as a table of numbers, and those numbers are going to be the coefficients of the terms. Like, for example, this one's going to be 2, this is going to be 2, this one's going to be 3, and this one right here, because there is sort of understood that there's a 1 there, we put a 1 there, okay? And we rewrite our expression in matrix form, okay? The reason that we do that is because a lot of the tools available at our disposal, like calculators or Excel or what have you, really like solving simultaneous equations in this fashion, okay? Now, mathematically, the way that you would solve it is we have essentially this is, we'll call this as like AX equals B, right? So we have this square matrix A times these unknowns equals B. The answer is to invert that square matrix and multiply it by B. And that's probably something that you at least saw in a algebra class, but you probably didn't do very much, because when you're first learning algebra, the idea is to learn the process, and so it's really easy to learn through substitution and elimination. But applying the process and applying it repetitively over and over again, it's a lot easier to just employ matrix algebra. And the nice thing about that is, again, a lot of our technology available to us, it makes this a lot easier. Another thing that's worth mentioning is that, inverting a 2 by 2 matrix, you can do that by hand pretty easily. There's a pattern, it's very rote. When you start getting into 3 by 3 systems or anything that's a little bit larger, it's pretty tough to kind of do that by hand. And that's why we let a calculator or let software do that for us. I won't bring up the dreaded MATLAB or anything, because I know when I bring up MATLAB, it begins the onset of acute post-traumatic stress disorder for civil engineers. But what I will say is that computers, really, they're these big fancy devices that do 2 things very well. They count and add. They just do it really, really fast. So writing math in this term or in this fashion makes it really easy for computers to solve. Now, I have here some info on how to solve a 2 by 2 system using a Casio. I actually have compiled a YouTube playlist, which I'll probably link to Blackboard, that goes through how to solve simultaneous systems of equations with other calculators. But I go through how to do it in the Casio in here, because we've integrated that into Engineering 111 and what have you. But if you're using a Casio, what you do is you go to mode 5, so you hit the mode button, go to mode 5, which is the equation solution mode. And you're going to use either mode 1 or mode 2. Mode 1 is for 2 by 2 systems, mode 2 is for 3 by 3 systems. And so when you go to mode 1, you get this sort of table that pops up, and what you do is, these terms over here, this term here and here, that's just the coefficient matrix, and the last column, this 3 and 4, comes from the coefficients on the right side of the expression. And so when you plug and chug, you get x is -1, you get y equals 2. And what I would say about this is that this is such a fundamental mathematical operation that a $20 calculator has this mode pre-built into it. It's that fundamental in the land of mathematics. So you go to mode 5 to solve these equations. Mode 3 is the quadratic, mode 4 is a cubic equation. And if you go to mode 1, that'll bring you back to basic operation of the calculator. Make sense? Okay. I want to have this background because I want to go into this example. Okay. So you'll see where I'm going when we get into this. But let's take a look at this example. Okay. So I have here this right here. I have here a truss, and I've got the reactions already figured out. This, I guess I'll call it a scissor truss. And there's kind of some problems with solving this truss by hand, because if we look at joint B and joint C, we can't solve those joints automatically. We can't do that. Okay. There's too many unknowns. And if we look at joint A and joint D, there are 2 unknowns. We could theoretically start with either one of those, But the problem is that they both contain diagonals. So there's really no way of solving this problem without having to deal with this, okay? And so I wanted to go through a little bit of this so that when I start writing equations of equilibrium, you kind of go, oh, okay, I see where this is coming from, okay? Now what I'm going to do is I'm going to solve joint A. I'm sort of picking joint A because I've got two reactions in A, and I actually want a joint that's a tad more involved because I kind of want you to see where everything's coming from. The hard part is setting it up. The simultaneous equations is actually the easy part. Okay, so let's sort of take our time with this. Now before we get into this, I kind of want to look at our slope ratios. Ratios. What's going on? There we go. Ratios. And I kind of want to look at it a little bit differently than I have in the past. So I'm gonna do this, and I'm gonna sort of split this up like that because I want to look at two different members. I want to look at member AB, and I want to look at member AC. Okay, so let's look at member AB. Okay, so member AB, we have this sort of slope ratio that's written kind of like this. We have a right triangle like that. And we're told that member AB is at a 1-to-1 slope ratio. So if this is 1-to-1, what's the hypotenuse? Ooh. Square root of 2. This is the square root of 2, right? This is 45, 45, 90. Now, up until now, we haven't actually looked at the hypotenuse, but we're going to need to do that when we write our equations of equilibrium. So what I would tell you is that the only time that you're looking at the hypotenuse in a fashion like this is when you're looking at two equations and two unknowns. All right. Now, I want to show you something. All right. I want to compare ABX. So let's take a look at this. Would you agree that ABX is to 1 as ABY is to 1? Would you agree with that? Okay. But I want to look at it a little differently. If ABX is to 1, what is AB? What would be the denominator here? Square root of 2. Like I propose that ABX is to 1 as AB is to square root of 2. So what I'm getting at is I propose that ABX is 1 over the square root of 2 AB. Would you agree with that? Okay, what about ABY? Is it going to be the same thing? ABY is to 1 as AB is to the square root of 2. So ABY is 1 over the square root of 2 AB. Does that make sense? Now, you might be going, that's great. Why does that matter? Don't worry, you'll see why it matters here in a second. Just bear with me for a second. Let's look at member AC. So member AC, we have member AC, and that is a 1-to-2 slope ratio. So what's my hypotenuse? Square root of 5. Okay. All right. So I propose then that ACX is to, what is that, 1 or 2? 2, as AC is to the square root of 5. So therefore, ACX is 2 over the square root of 5 AC. Does that make sense? Everybody with me on that? And then ACY is to 1 as AC is to the square root of 5. So therefore, ACY is 1 over the square root of 5 AC. So I'm doing something a little different than I did before. I'm writing the x and y components in terms of the hypotenuse. I wasn't doing that before. This is a little new, okay? So the denominator for all of these fractions is the hypotenuse, okay? With me so far? Okay. Now, if you're okay with that, I want to look at the method of joints at A. Okay. Now, before I analyze this joint, I'm going to make a blanket statement, okay? Okay? I'm going to assume both members are in tension, okay? I'm going to do that because I'm going to let the math sort of do the work for me. If I assume they're both in tension, what that tells me is that when I solve this out, if I get a positive answer, that means that assumption is correct and it is in tension. If I get a negative answer, it just means it's in compression, okay? So, whenever you're doing math like this, it's a lot easier to just make blanket assumptions and let the math work itself out. You'll see what I mean here in a second, okay? So let's draw our joint out. Okay, let's put our joint right here, and we have a member like this and a member like this. Now let's not forget that we have a 40 kip load right here and a vertical load that is 25 kips. Okay. And then I'm going to have this, and this, this, and this. Now again, we're assuming tension. So tension, 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 tension. Pulling away from the joint. Let's name these. Let's call this ABY, ABX, ACY, ACX. Okay, so far so good? All right. Now, let's apply equations of equilibrium. Let's start out with sum of the forces in the x direction. Okay, so I'm going to sum forces in the x direction. Okay, let's see what we get. So do I have any forces that are going to the left? I got 40 kips, right? So 40 kips. So 40 kips is going to the left. What do I have going to the right? What does my free body diagram have indicating going to the right? I have ABX and I have ACX, right? But ABX and ACX, I have answers for. See, I have a new expression for this. Instead of ABX, I'm going to write 1 over the square root of 2 AB. Instead of ACX, I'm going to write 2 over the square root of 5 AC. So you starting to see where these came in? I'm substituting. I'm writing in terms of my real unknowns. See, my actual unknowns with the members are AB and AC. The x and y components are just a function of those. So I'm getting to the actual, the raw unknowns, which in this case are the actual AB and the actual AC. So what I'm getting is I'm getting 40 kips equals 1 over the square root of 2 AB plus 2 over the square root of 5 AC. Okay? Now we've had situations like this before where we applied equation of equilibrium, we actually didn't get an answer, right? When we were doing reactions, we were solving for reactions and we had internal hinges, like we would get something like this and it wouldn't actually give us an answer. So I'm going to give this a name, I'm going to call this equation 1, okay? In fact, what I'm going to do is I'm going to write this up here on the board. So we'll say equation 1, we'll say 1 over the square root of 2 AB plus 2 over the square root of 5 AC is 40. With me so far? Okay. So I think it's probably a foregone conclusion we are going to have an equation 2. So what's going to happen here is we're going to get that by summing forces in the y direction. Now here's the thing with the sum of the forces in the y direction. All the forces are going up, right? Because we have an ABY we have an ACY, which is 1 over the square root of 5. Again, that bookkeeping's getting tested a little bit. And we have 25 kips going up. So we've got 1 over the square root of 2 AB plus 1 over the square root of 5 AC plus 25 kips is 0, or now we have a new equation. So now here's our next equation. So now we have So now this is what I meant. We have 2 equations, 2 unknowns. Now unlike this one, the simultaneous equations, the coefficients sometimes aren't that pretty. We don't have 1s and 2s. I mean, we can maybe handle that with substitution and elimination. Sometimes I think it's a little easier to just solve using the technology. Okay, so I'll show you a couple different ways. So in matrix form, I'm going to rewrite this. And the way I'm going to write it is I'm going to say we have 1 over the square root of 2, 2 over the square root of 5, 1 over the square root of 2, 1 over the square root of 5, equals 40 and minus 25. Okay? So all I'm doing is I'm taking these coefficients, putting them in a square matrix, taking these 2, putting them in a column. Okay? Now I'll show you 2 different ways to solve it. Okay? The first, break out the Casio FX115 ES Plus. So I even have a little simulator for that right here. Alright, so I'll show you how this works. So we go to mode 5, equation 1, and what we're doing is we just enter in our terms and press enter. So what do we have? We have 1 divided by the square root of 2, enter. 2 divided by the square root of 5, enter. 40, enter, or press the equals marks. 1 divided by root of 2, enter. 1 divided by root of 5, enter. And then negative 25, enter. And so what should happen is you should have a table set up like this. And what you can do is you can just press equals again, and boom, here we go. So let's put this over here, right? Okay, so what we'll say is using the Casio, let's just like raw write what the Casio yielded. So x equals minus 127.8 279 2206. Then if I press equals again, y is positive 145.3444185. Okay? So how do I interpret that? Okay? Well, the Casio doesn't know what we called AB, what we called AC. It doesn't understand. But it does know that the solution X and Y is in order. And we wrote AB first and AC second. Okay? So what that means is, therefore, AB is negative 127.3 kips, or 127.3 kips in what? Compression or tension? Compression. And it's in compression. Why is it in compression? Because it's negative, and we assumed that all the forces were in tension. So if it's negative, it's in compression. This is what I meant when I said just let the math do the work. Okay? And AC is plus 145.3 kips, or 145.3 kips in tension. Okay? Another thing that you can do if you want, you're an engineer, so you should love Excel. So I'll say, using Excel, what I'll say is you want M inverse and M mult. And I'll show you real quick. I'll show you real quick how that works. Okay? And then we'll get forward. Now, I am recording this, so if we go a little fast, we can always go back. But I'll just show you in case you're interested. All right, so, and again, I can bring up MATLAB if you would like. That's what I thought. Okay. Now, what I'm going to do is I'm going to enter in those matrices. So, all right, so then we've got, it's supposed to be 2. Kind of dark here on the screen. So. And that one's 1. And then over here, 40 and minus 25, right? Okay. So what you can do is, the first thing what we'll do is we need to take the inverse of that. And so when you take the inverse, press enter. What happens is, because you're doing a calculation to a big region, this is called an array calculation. So if you ever like click this cell right here, you'll kind of see that it's highlighting that whole region. So then the next thing you do is multiply the first one by the second one. And by golly gosh, you get the same answer. So there's 2 ways of doing it, right? So M inverse and M mult. Either one will give you the same thing. So, make sense? All right, any questions on this? And like I said, I have a playlist where I found a couple of different YouTube videos on how to do it on like a TI-84 and TI-36, a couple other things, and I'll post that. Okay. Any questions? All right, so before we move on to the method of sections on Wednesday, I kind of want to talk about zero force members, okay? Now, when you all were doing, I'll be honest, I can't remember on the last 2 problems, but were there any homework problems that had zero force members? I can't remember if there were, but I know that there was that in-class example that had a zero force member right in the middle, right? Now, what if I told you that I could have just looked at that truss and told you it was going to be a zero force member without doing any math? I just look at it. I'm going to show you all how to do that as well, but I think the first question that I usually get is from students is, so hold on, why would you put a member in a truss that doesn't have any force in it, right? And that's a fair question, because think, any truss member, any member that you insert into a truss is going to cost money, right? That's holes you've got to drill, that's extra members, it's more you got to put together, that just takes money. So why would you do that? Why do you have zero force members in a truss anyways? Well, there are two primary reasons why you would have a zero force member, okay? The first is that the member might be serving as a brace. So if you take me for steel design, what you'll find is that when we design members for tension, when we design steel elements for tension, we're trying to ensure that members don't yield, exceed their yielding strength or their fracture strength. But that's members in tension. Members in compression like to buckle, okay? And one of the ways that we can increase the buckling strength of a given member is to put a brace in the middle of it. And so that truss member might not be there to support load, it might be there to act as a brace for a member in compression. That is one practical reason why you would have a zero force member in a real structure. But the other, and this is also going to be very true in here, is that the zero force members might only be zero force members for the loads in a given position. What if the loads move? You know, here's a truss, I've got loads here, and I've got some zero force members. What if the loads move? Okay? And what type of structures do you think we care about when we're talking about loads that move?
Vehicles.
And what type of structure?
Bridges.
Bridges, right? So in bridges. So what you might find for a truss is that for a given member in the truss, that truss member may not be carrying load if the load is here, but if the truck moves over here, then suddenly it carries forces. And so that's another way I want you to think about zero force members. We also are going to have some energy-based solutions here a little later where we have to solve the truss multiple times. Okay, you might get some zero force members. Now I have here an image of a truss below, and what if I told you without doing any math, I could tell you that member, that member, that one, that one, that one, that one, that one, they're all zero force members without doing any math, okay? And I propose that everybody in here will be able to do that if you follow three simple rules. Two of the rules are kind of the same, but I like splitting them up because I think they make it easy to identify geometrically. Okay, so here are the three rules that you need to follow. The first rule is I'm calling the no load applied at the joint rule. So if you have a truss joint like this, and there's two members framing into that joint, and there are no loads applied to that joint, this member and this member are a zero force member, okay? And to be clear, there's nothing like inherently magical about me making that observation. Let's look at this joint. Let's just look at this joint right here. Let's apply equations of equilibrium. So this has a horizontal unknown, this has a horizontal and a vertical unknown, right? So let's sum forces in the y direction. What's the vertical component of this going to be? 0, right? If the vertical component is 0, then the horizontal component is 0. So that's a zero force member. Then all I've got is this, and if I sum forces in the x direction, that's 0, right? So there's nothing magical about that. I propose that if you have a joint that has two unknown members and everything else is 0, those two members are 0. And that also holds true if I've got a joint like this that has 4 members framing into it, and I've already figured out that is a zero force member. Zero force members. That's rule 1. Does that make sense? Let's talk about rule 2. Rule 2 is if you have two members, but you have collinear loads. Okay? So let's look at this one right here, right here in the top right. Okay? So I have a joint, right? And I've got two members in that joint, and I've got a single load applied, and that load is collinear with this member. Okay? So let's say I got 20 kips going to the right. I propose that equilibrium tells me that if this is 20 kips to the right, that's 20 kips to the left, and that's 0. And how did I come to that determination? By summing forces in the y direction. Okay? If I sum forces in the y direction, this has a vertical and a horizontal component. There are no loads going up and down. So this vertical component has to be 0, so the horizontal one has to be 0. So that's a zero force member. Okay? Now there's a couple other places where that can happen. This is a good example of one. So if you have a truss component like this and you have a roller going like that, so this reaction here is totally supported by this member, that's a zero force member. Okay? And again, that also can hold true if the truss joint's rotated or if you've got other members framing in that have already been determined to be zero force members. Does that make sense? Now to be clear, this analogy doesn't hold true if there's 3 members framing in because the rule is 2 members framing in, not 3. Sound good? Last rule, if I have a joint like this, a joint like this where I have 3 members, no external loads, but 2 of the members are parallel, this member equals this one, that one's 0. How did I do that? Again, sum of forces in the y direction. The vertical component's got to be 0, so the horizontal component's got to be 0. Okay? Make sense? Let me show you this in practice. Let's take a look at this example. Okay? I want to look at this truss, and I want to see if we can identify some zero force members on this truss without doing any analysis, any math, just looking at it. Okay? And so the best way of doing that is to look at the structure joint by joint and see if there are any joints that we can identify that will screen zero force members. Now, before I do that, I'm going to say we have a vertical reaction right here. I'm going to say we have a horizontal reaction right here and a horizontal reaction right here. The directions of those reactions don't really matter, like this one in G could be going to the left or to the right. Doesn't really matter, just as long as I've identified that it's actually there. Okay? Let me ask you a question. Is there any joint that we ought to look at? Tell you what, is there a Rule 1 joint that we should look at? What was Rule 1? Rule 1 said that if you had a joint with two unknowns and no loads applied. Let's look at joint D. Okay, so joint D, we have two members framing into joint D and there's no external loads applied. So what does that tell me? This one and this one are zero force members. Zero force member, zero force member. No math, just zero. Guaranteed. Okay. Anybody see another joint that we ought to focus on? We looked at joint D. Let me circle that. What about now? Any other joints that we ought to look at? G. Okay. So you're asking me to look at G. Why are you asking me to look at G? Well, the Rule 3 or 2, we can quibble on that, but what member are you looking at? What member screams out zero force member to you? Well, let me ask you a question. Let's look at joint G. So if I sum forces in the x direction, what does that tell me? It tells me this member. Sum forces in the y direction tells me this member. Now, what can you see at joint G?
There's no Y reaction.
There's no vertical reaction. So if there's no vertical reaction, what does that tell me about the forces in this joint? What's going on with it? Which is the zero force member? AG. That's the zero force member. Zero force member. Does that make sense? Okay. So we've looked at joint G, joint D. Any other letters that we should look at? Because there's two more zero force members in this truss. There's two more. What's that? What's that?
Isn't it have to E one of them?
Okay, now how'd you come up with that?
E's straight down.
Straight. That's right. So joint E, we have a vertical load going downward, right? So this member, so what's the force in this member? In member CE. This is 50 kips down, this has got to be 50 kips up. So this is 50 kips in tension. But what about that member? That's zero, right? Because this is zero, there's nothing going horizontal. This right here, that's a zero force member right there. There's one more in there. There's one more zero force member in this truss.
Is AH zero?
AH, you're on the right track, but it's not AH. Look at joint H.
HB.
HB. Why? I say here that all the diagonals are at a 1-to-1 slope ratio. If they're all at a 1-to-1 slope ratio, then what can you tell me about AH and HF? They're parallel, right? And if they're parallel, this force and this force is the same, and that one is 0. I don't think you can quite say the same about AH because there's a vertical and a horizontal reaction right here, right? So we can't quite say that the sum of the forces in the y direction is 0. So I bet this has got some load and I bet that's got some load. Does that make sense? So look at this. We got 1, 2, 3, 4, 5 members that we've analyzed. We didn't do any math. Now, if you think that this is like not practical, that you wouldn't have many trusses where this would happen, when we start looking at truss deflections, this will happen, okay? Because in order to compute truss deflections, you have to analyze the truss twice. You have to analyze the truss for the loads that are on the truss, and then you remove all those loads, and you put a single load where you're interested in finding deflections. So you got this big old truss that only has one load on it. So can you get some zero force members in that system? You bet. So this is a skill that it actually will generate some dividends, okay? Does that make sense? So we are gonna see this in the not too distant future. All right, so let me make sure I got them all. I think I got them all because I put the solution in the slides. It'd be embarrassing if I didn't get them all. Yep, I got them all. Look at me. It's like I know how to do this stuff. Barely. All right. Any questions? All right, so you all have a homework assignment. The homework assignment is to do simultaneous equations on a joint. And I think I even gave you the reactions on that joint to make it a little easier. I want that part to be kind of, I want you to be comfortable with that. Then we're going to do one lecture on the method of sections. And then we get into energy methods. Energy methods is a little different. It's definitely new. For some of you, this might be a statics review up until now, but energy methods is going to be very new. And then we will tackle that on Friday. That's all I got. I will see you all on Wednesday.